completely different characteristics and completely different distributions. So what you want is to separate those again, so you can exploit the individual structure in each of those data types. Yeah. So how can we improve this? How can we separate this? The idea is the same one as before, actually. We try to group data that sticks together, that belongs together. And we don't want to have to store some elaborate metadata that tells us how to decode this again and put this back into normal x86 code. There are several reasons for this. One main reason is that you want this to be reversible, because it can always happen that, yeah, someone has a jump table or whatever in your code section where it doesn't really belong, but it's just random data in your code section, and you want to be at least able, yeah, to still decode this correctly anyway. So you need some mechanisms to decode that, but you want it without additional overhead. And can we get away without storing any metadata that stores us how to decode this in an efficient way? Well, I wouldn't be mentioning this if you couldn't, but you try to stay with the basic opcode encoding, because the processor can decode it, so we can too, and it also means that we don't have to do any additional processing after the reordering stage. We don't have to translate that back into executable code again. After we've undone the reordering, yeah, you can just jump into it and execute it. But we try to split it into several streams. To do that, to find out which one of those bytes, which is everything the processor actually sees, this byte stream, is an instruction, which one is an address, which one is a displacement, you need a disassembler. It doesn't need to be a perfect disassembler. It doesn't need to be able to give you instruction names of the actual encodings. And some things like prefix bytes, you can just treat those as if they were individual instructions. But it needs to be able to determine what type of data is what. What is an opcode? What is instruction data? What is address offsets and so on. And you need to be able to determine instruction sizes so they don't get out of sync. This sounds like a total overkill, because writing a disassembler just to be able to pack some code, this really sounds like overkill. But you don't need much information. You just need a bit of flex, actually. And what I do in Crunchy is a very simple table-driven disassembler that fits into about 200 bytes, plus another 256 bytes of tables. That are everything I need to disassemble x86 code approximately. This is not perfect, but it's reversible, and that's enough if you're doing compression. So, another interesting point is call instructions when you're calling subroutines. This is important because when you have a high-level language code, you call a lot of functions. Most of your code lines are probably calling functions in one way or the other. So this happens a lot, and those call opcodes are quite big. This is 1 byte for the actual operation that tells the processor now's the call coming up, and there's 4 bytes, which is a relative offset to where should I jump from here, how far to get where I want to be. This is relative, so it's no problem to move programs in memory. That was the original idea. If you have to load a program at a different address, you can do so without having to patch every single call, because the relative offsets don't change if you just move it. But it hurts compression, because usually some functions get called very often, others just get called a few times. But those that get called several times, you would expect to get some gains in that, because it's this call-up code and the same address, and you have that several times, so you would expect some compression. But with a relative offset, the offset you see for this call instruction is different every time a function is called, because it changes every time. So relative offsets are different each time. So you transform that back to absolute offsets by just adding the position of the opcode back where it is in the source file. This improves compression by a few percent. I didn't have the time to prepare actual numbers, because it's actually relatively hard for me to test, because I only have the sophisticated code filtering software, and I don't have old versions lying around anymore. And would have been a real work to just turn that back into the basic one, so it can tell you the exact ratio, but it was a few percent, 3% or so improvement. And this kind of technique is used by UPX and other similar exit packers. But we can also take that one step further, because a lot of those functions get called several times. You don't, even if the offset is the same every time, you don't want to code it every time by itself. What you do, you keep a list of locations that got called in the recent past. Doesn't even have to be unique. You can have the same entry into multiple points in this list. Doesn't matter. This makes list management a bit easier. And if this offset is in the list, you just code the index in this list instead of the actual offset, which is a 1 byte or even smaller index instead of a whole 32-bit address. And doing this on this already absolute transform gives you another 2% code size improvement after packing. And still, we're not through, because you can, when you have that kind of logic, where you actually try to exploit the structure of how call instructions look, you can go even further and look at how functions look, because those are most likely call targets. Functions are what you're trying to call. And if you're using the Visual C++ compiler, like we do, for example, the spaces between functions get padded with a few breakpoint instructions, which is just there so you notice an error if you accidentally, by some way or other, jump somewhere you shouldn't between functions. The idea is just that you catch this kind of bug. But you can, this kind of opcode wouldn't be executed in normal code flow. But you can use that to determine where functions start, because each time you have this padding with breakpoint opcodes, you know, okay, the next non-padding thing we're going to see is probably the start address of a function. So when we see some padding sequence, we just add the end of this padding as a potential call address and hope that it is actually a call address. In the worst case, it's just happens to be that you actually use this breakpoint opcode somewhere in your program, and that entry will not be used. So you lose one table entry, and it's not really a big deal. But that way, we can usually predict call targets even before they first get called, so we can have a good guess about what's going to be a function and what's not, even though it's never been called. Actual hit rates for this are very high, and most intros are packed with Crunchy. Have done some checks. You get a 92% hit rate on this. So 92% of all calls are encoded with a complete offset, but only with this index number, because either we found it first, or on the second call it gets coded with that index. So this really helps a lot, and it gives you another 1.5% improvement on top of everything else we already had. By this point, we've saved, for example, on Candytron, by this point you've saved about 3.5 kilobytes just by reordering call addresses and storing them in a different way, which is not that much code to undo. This is just a small table and some assembly code to undo it. So it's very simple, and it gives you a great gain. Okay, so that's the end of that example, and we're close to the end of the talk. I'm just going to sum up things for the end. And I gave you lots of rough introductions as to how different compression algorithms work, what they are trying to do, and it's not that important that you understand all the details. If you look at most compression papers, they are terribly hung up in the details, but they don't actually tell you what it is trying to do. For example, this code reordering thing, that was not my idea. I got that from a paper that tried to do this in a context modeling framework. And all it's doing really is trying to split those instruction streams. But the way they described it was a lot of stochastic models and very complicated terminology, so it's hard to read, but the idea is really quite simple. It's the same all over the literature, so you have to be careful when reading that kind of stuff. It's usually fancier than it has to be. And just don't get too much into this when you just